All right. Sorry, I'm a little behind here, but we can get started, and we are recording. All right. So today we are, what are we doing? Lecture 11. So we're going to continue our discussion of inferential approaches, thinking about causal models. And today we're going to learn a couple techniques building off of the foundation that we built last time to think about how we can actually do identification in practice. And so we're going to learn a couple of techniques that we can employ to do identification and get around some of these problems that we identified and difficulties in doing that last time. So I actually wanted to start with this example that I started with last time, where we talked about health, consciousness, brushing teeth, going to gum disease, going to inflammatory response, and this ultimately goes to heart disease. And we had two other ways of getting there, two other paths. We talked about diet, right? And exercise. Okay, and the treatment we're interested in is brushing teeth, right? So this is treatment. And our response is here. Okay. And so at the very end of the lecture last time, we talked about kind of good paths and bad paths, backdoor paths, front door paths, right? And if the causal diagram represented here were kind of exactly the right sort of model of truth in the world, then we could actually build a pretty simple model to determine the effect of the treatment on the response, right? So heart disease. And one of the ways that I talked about doing this is, okay, what's a problem here if I wanted to just do something like heart disease is equal to beta brushing teeth. Who can help me elucidate some problems? Yeah, Christopher.
I forget what you call them. There's a couple of mediators in the way. You've got gum disease and inflammatory response that are sort of part of the path from your treatment to your response.
Yes, except that if you control for a mediator, does that open the path or does that close the path?
Could you explain again what you mean by control? You just mean like to hold it constant?
Controlling for a variable means that you are able to accommodate the variation that that variable introduces into your sort of system. And yeah, traditionally the way that we would control for the variable would be to like include it in the regression.
Just make it part of your model. So you're basing your result off of that as well.
Yeah, and so what happens when we control for a mediator to the path? Anyone remember from last time? The path, it doesn't it doesn't disappear, but you actually close the path. So you go from a good path to a bad path. Okay. So actually, if you were to include either gum disease or inflammatory response into that equation, you would actually close the path, and you could no longer, you are no longer able to distinguish the isolated effect of brushing teeth on heart disease.
Why would it close the path? It no longer has variation. Or is the variable?
Okay, so where was my?
I guess I hear a lot of. I hear the term like to control for something a lot, but I don't actually know what it means. Like, how is that accomplished, I guess?
So, okay, controlling, right, means that you are adding in the variable into your model, right? And what you're essentially saying is the variation from that variable is related to the variation in my output. And by adding it, I have now related the two, and so you're controlling, right, for how the variation in one variable impacts variation upstream.
Okay, thank you.
Yeah. So essentially the problem is adding in a mediator, you have kind of this confounding effect where you have correlated variables both attributing to an output, right?
You wouldn't really know what the effect of gum disease or inflammatory response was if you included both.
Yeah.
They both have variation.
Yeah, so you typically assume some kind of independence of your explanatory variables. And so now you've got these two things both affecting heart disease, right? And then it's probably going to misattribute the effect of one or the other, which is going to cause your treatment effect to be inaccurate, okay? So we usually would not want to be including mediator variables, typically.
Or at least more than one.
Yeah, any number of mediator variables. If it's a mediator variable, you typically don't want to include that in your regression, okay? All right. So, what are the paths from our treatment to our response? Yeah.
Brushing teeth to the gum disease to inflammatory response, and then diet to heart disease and exercise to
Well, yeah, brushing teeth to health consciousness, to diet, to there, and then brushing teeth, health consciousness, exercise to there. So what is this path called, and what is those paths called? Does anyone remember? Nobody? No one remembers from last time? Right at the end, we talked about some types of doors. Front doors and back doors. So which one's front door? This one, and then the other two are back doors. Okay. And how do we close a backdoor path? So, all you have to do to close a backdoor path is control for the variation in your backdoor. So, we could do something like this, plus beta 2 diet, plus beta 3 exercise. So, let's see. These close the back door. Okay. And so if you have a causal diagram like this, then this regression would actually give you the causal effect of brushing your teeth on heart disease. Okay. So the idea here is to keep your front door open, and we do that by not controlling for any of the mediators. And then we want to close the back doors by controlling for variables in the path of the back door. Okay. So the general idea is to be able to set up a causal diagram in order to inform kind of how you structure the model, right? And it's important to do so because we don't necessarily just want to throw in all of the variables, because if you just throw in gum disease, inflammatory response, diet, and exercise, in that case, you would actually not have a good measurement for treatment. Yeah.
So in order to do this, you basically already have to have some kind of knowledge, like what kind of how the causality could be before, like setting all this up and then drawing this diagram. But what do I do if I like don't really know before how the causality chain or whatever could be? Like if I just have a bunch of variables and like a response.
Yeah. I would actually say there isn't a great way around this, right? Because you need to make some assumptions about what the relationships between the variables are. And it may be the case that you actually get counterintuitive results, which may make you kind of rethink whether the causal mechanisms are set up appropriately. But this is where the art of it comes into play, that you can't really get around, which is that you will always inherently have to be making assumptions about some of the relationships in order to, design a good causal study. And a lot of the rigor and robustness of that causal model is something that you'll need to be able to defend, right? You'll need to be able to justify this kind of relationship structure. Yeah.
With the backdoor paths, would you call, I guess, diet and exercise like the beginning of the backdoor paths?
No. I think you always start with the treatment.
I guess I'm trying to understand how you knew that diet and exercise should be what you include to close the back door.
Oh, it doesn't have to be that. So all the necessary thing to close is anything along the path starting from your treatment. So anything between treatment and heart disease, any variable that you have data on or have some control over, that's what you would want to use to close the path.
And you close paths by controlling for a variable on that path.
Yes.
Isn't closing a path, I guess, there's no variation in that variable? Like, or at least I guess there's at least one variable with no variation.
So the idea, right, is that if I didn't control for these paths, right, then I will say something like, I'm brushing my teeth and I observe a health disease outcome. But that health disease outcome could have been coming from other aspects related to a person's like health consciousness, such as how much they ate and how much they exercised, right? And if I only include brushing teeth, the outcome of heart disease, and I'm attributing everything to just brushing my teeth, well, I don't know anything about how diet and exercise contributed to my heart disease, right? But if I control for diet and exercise, that cuts off all the ways that health consciousness could be affecting heart disease besides brushing my teeth, right? So imagine a case where, for simplicity, let's get rid of exercise for a second. Let's get rid of exercise for a second. And you say, I observe a bunch of people brushing their teeth, and they all have lower heart disease compared to a bunch of people who don't brush their teeth. But you didn't control for diet, right? And then your conclusion might be, well, brushing your teeth reduces incidence of heart disease by, however much. But it just so happens that all the same people who are brushing their teeth very actively also have a healthy diet, right? And in that case, if you were to control for that, maybe it would say, oh, actually your heart disease is mostly attributed to the healthy diet, right? And that in fact brushing your teeth has a much sort of smaller effect on heart disease once you actually control for the diet. Okay?
If the treatment we were interested in, like primary treatment or exercise,
Yeah.
and we were just controlling for the other two paths,
Yep.
would it still be bad to include mediator variables? Or
No,
would
there wouldn't be a mediator variable, because remember, a mediator is a variable in between your treatment and outcome that isn't affected by anything else,
Okay.
right? And so, is there any variables in between here? No, right? These would not be considered mediators anymore because that's our treatment and not that. So mediator is specifically thinking about things between your treatment and your outcome.
Okay, so we could include toothbrushing and these.
Yeah, so if exercise was the treatment, then you could include multiple of these variables. You wouldn't need to, technically. We would actually call that, we might actually think of some of these as redundant. But yeah, you could. And part of the reason why I talk about them being redundant, you have the same thing where they might be correlated. If you include multiple ones, like let's say the effect of any one of these variables on heart disease might confound with each other, but we don't actually care that happens, that like our coefficients on these guys would not be correct, because the only thing you really care about is the treatment effect on exercise. Yeah. Okay. So in this particular case, I think this kind of setup is primarily meant to get you guys to, yeah, again, think about how to properly structure the model and not just throw all the variables in, because once you have this idea of what the relationship is, you'll be able to, create a defensible model. Now, who actually thinks that this is a good causal diagram? Probably, it's probably a little bit simplistic, right? And so you could imagine that there could be other factors that might influence gum disease or inflammatory response, or other factors that may relate to things on other paths, right? And you could have much more complex things. And so the idea that you could, even if I get rid of all this stuff, generally the idea that you could control for let me see. The ability to go from your treatment to an outcome and cut off all of the possible backdoor paths just by, I think we call this by like backdoor proxy, which is like cutting all the backdoor paths off, is like pretty unrealistic, right? There's so many unobservable effects, that relate to other things that might affect your outcome, that it's highly unlikely that you'd just be able to control for and have the data to be able to just cut all the backdoor paths and get a nice clean thing like this equation. Okay. And so in reality, there have been a handful of identification tools that let us leverage particular things about models and data that give us kind of a better chance at being able to do identification and get around this like bigger question. Okay, and so those are the tools that we're going to talk about today. Okay, any questions? Yeah.
So you have the equation sort of sketched out there?
Yes.
But we use closed paths in similar ways for mediator as well as backdoor.
Mm-hmm.
But it looks like in the mechanics of using closed, when you close the backdoor, you're actually controlling for the variables by adding them into the equation, so you can control for them. But when you close the mediator path, you're not actually adding the variables, but we're using closed.
No. You want to keep. The thing is, you want to keep the direct path between your treatment and your outcome open, so we don't include the mediators.
Okay.
Generally, including and controlling for a variable will close a path.
Okay.
Unless it's a collider.
Okay.
Yeah. Yes.
Why is that? Why does a path close when you control for a variable?
Okay, I think I was just explaining this, right? So with health consciousness, if I don't include diet, right, and I only include brushing teeth, then everything related to this outcome is being attributed to brushing your teeth, right? So if I only include beta 1, brushing teeth, then we're saying everything that varies in heart disease is related to the variation of brushing your teeth. If I only include diet, then you're saying only diet affects your outcome of heart disease, right? And if I include both, you're saying both things have an effect on your heart disease outcome. Make sense?
Yes, what you just said made sense. But I guess maybe, I don't know, maybe you already explained it. The abstraction of closing a path by controlling for a variable doesn't make sense, but maybe I'll pick it up as we go along.
Yeah, maybe we can talk about it separately. Okay, let's think about potential tools for identification. The first one we'll talk about is known as fixed effects. So this is a method for controlling all variables observed or not, which is one of the really powerful things about fixed effects, is it can actually tell you a lot about variable effects that may not necessarily be observed. As long as they stay constant within a larger category. Okay. So let's consider an example of weight as it relates to exercise. And let's say that you go around and you randomly sample a whole bunch of people in the population, and you observe how much they exercise, and you may even get some people to change how they exercise over time. Okay, and so we're really interested in this treatment effect of how much someone exercises compared to how much they weigh. Well, so what other things may affect somebody's weight? Yeah.
Diet and genetics.
Okay. And so with genetics, maybe we'll say something like race, maybe we'll say gender.
Family medical history?
Yeah, so you may have basically a whole bunch of other factors that are related to the individual. Yeah, so what are we talking about? So diet, so I'll say broader genetics. You could, like, their birth city, the amount of education that they have. Yeah, sure, height. Okay. And so we've come up with a kind of broad list of individual factors. Okay? I'm going to leave out diet for the purposes of this particular example. And if I were to draw a sort of causal diagram, I might have something that looks like this. So exercise and going to weight and individual factors that go to weight and maybe even can affect how much you exercise as well, right? Okay. And so remember in this cloud of things, there could be all these things like race, gender, you know, where you're born, your education, your height, whatever, your broader genetics. These are all plausible sort of backdoor paths, right, to go from exercise to weight, right? Because there are other things that affect weight that ideally you would want to control for, right? And so we could think about this in a similar way as our other example where we just control for those things, right? But like, is this list of things comprehensive in terms of all the possible individual factors? Probably not, right? But there's something interesting about this data. And actually, let me add in a little subscript T here, telling us about maybe how much these things change. Okay, if I were to look at the actual like data set that's attributed to, or that might be connected to something like this, I might see, you know, with this particular example, IT will have like weight, how much they exercise, race, gender, you know, birth city, etc. Okay, and so I'm going to write these in slightly different colors. So maybe for individual, so I is in reference to an individual. So actually I should probably have I up in the equation as well. So you have IT. You may have several observations over time about how much they weigh, A, B, C, D, E, F. Okay, and their race might be X1, their gender might be Y1, birth city might be Z1. And then for individual 2, you might see something similar. 1, 2, 3. Let's see, G, H, I, J, K, L. And then here you have X2, Y2, Z2. And then lastly, we'll have individual 3, 1, 2, 3, L, M, N, O, P, Q, R.
What's T?
T is time. So you may have several observations of an individual over time. Okay, so you get the point here. Okay, so what do you guys notice about this data? Anything interesting?
It all looks constant besides exercise.
Yeah, that's right. So if I were to look at these things, you'll actually notice, right, like a person's race, their gender, their birth city, none of these variables are actually changing over time, right? And so these are the same for individual I. So in this particular case, our fixed effects captures all of this plus all unobserved terms that don't vary over time. Okay, so you can imagine that if I actually just include a dummy variable for each individual, that dummy variable would capture all of the variation in that between groups that don't change over time, right? It has to follow this property where the variation does not vary within the group for the subset index that you're interested in observing variation over. And so in this particular case, we're leveraging variations in time for weight and exercise. And in fact, doing this controls not only for race, so including essentially, so one of the ways that you can think about this conceptually, but is actually not commonly done this way, is if you were to include a dummy variable for every individual, that not only captures all aspects of race, gender, birth city, but anything else related to the individual, right, that isn't changing over time. Okay, and so in that case, you know, this idea of like cutting off all the possible backdoors, now you not only don't need to have the data, you don't necessarily even need to figure out all of the sort of factors that might be creating a backdoor to weight, because you've kind of instantly covered all of them, okay? And that's kind of the sort of justification for these fixed effects. Okay. Any questions about that? Good question. So there are two ways to do this. So commonly, these are the two common ways of denoting this. So one is what I just mentioned. So you add a binary control variable for every individual. So this might be something like yit is equal to beta 0 plus beta 1 xit plus you have, let's say, a big beta, let me write it this way, plus the sum for, let's say, j equals 1 up to n, and you'll have something like beta j times dj plus epsilon it, where j represents every individual, right? So all you're doing is you're adding in a dummy variable for every individual. And you'll notice that that doesn't vary with T. This is more rare to see it structured this way, especially if you have more individuals. Right, and the reason for that is, right, are you really going to interpret all those coefficients? Right, we really care about the effect of the treatment, exercise on your weight. If you have like 1,000 individuals, are you really gonna go and say something about how each individual has some, related outcome on your weight? Is probably not really relevant to what you're trying to study. Yeah, so the idea is more that the individuals are acting as controls. We don't care so much about the effects of the controls. And also it creates a pretty messy model when you've got a lot of dummies. Okay? So, the other way is to de-mean variables by extracting within variation. So that looks something like this. YIT minus the average in YI is equal to beta 0 plus beta 1 x IT minus xi. Okay. So this is a different way of thinking about it, but we'll give you actually exactly the same answer. So beta 1 here will match the beta 1 of the example where we are adding a binary control variable for every individual. But what's happening here is essentially you're basically saying, okay, let me look at a particular individual and let me look at how much they weigh over time. Let me take the average of that weight and only observe how much the weight changes, right, compared to the average weight. And so, let's say someone weighs, 200 pounds, and you observe they go from 190 up to 200 up to 210. The average of those weights is 200, and so you demean everything. So all you would see in the actual inputs would be positive 10, 0, and negative 10. Okay, and then in the exercise, they may have a high level of baseline of exercise or a low level of baseline, and you are demeaning it. In essence, you are taking the average of how much they exercise and just seeing within how much, within that particular individual, what is the change in the exercise. And so that's called demeaning, okay? And if you think about what that does is, for someone who weighs 200 pounds, they may have that base level of 200 pounds because of their particular gender and race and all these things related to their individual, but then you are isolating, we get rid of this 200 and just see how much they're changing based off how much they're exercising. So this normalizes all the individuals to just look at the changes in the weight as it relates to the changes in how much they exercise. Okay, And it turns out doing this is exactly the same as doing it with adding the binary control variable. Okay? Any questions?
It is like average yi. Do we take like the average between different
You take the average across times for each individual.
and then average among different individuals?
No. So it transforms this data set into IT. I'm going to call it weight DM for demeaned, and then exercise DM for demeaned, right? And so you would see something like this: 1, 1, 1, 1, 2, 3, and weight demeaned would be A minus A plus B plus C over 3. And then it would be B minus A plus B plus C over 3. And then C minus A plus B plus C over 3. Does that make sense? Yeah, so you are demeaning within each individual. All right. So yeah, this is, I'm gonna run through this a little bit faster because we have a lot to get through here. But I'll describe kind of what's going on, and then the code will obviously be available in a little bit. So we're going to look at a particular example of fixed effects, and all this is we are looking at a particular model where you're trying to understand the life expectancy and let me see. We're looking at how a country's economy measured in terms of GDP per capita relates to life expectancy, or specifically how changes in a country's GDP relate to changes in life expectancy, right? And you might observe, let me actually jump back to so if I have something like this, GDP, life expectancy, and if I have some data that might look like this, okay. And so each color represents a different country. Then you might see some kind of fit that looks like this, but in fact, the actual trend might differ between countries due to other factors besides the sort of economics. And so we would want to control for those to extract the specific trend. And so that's what this particular example is looking at. So you can see in this particular line of code, it is doing the demeaning thing. And so it is taking my observation minus the average of that within each group. And I'll let you guys kind of look at that code and figure it out. But the idea is, yeah, it's measuring that. Okay, and so here, basically, I have taken the demeaned data and I've run the regression where the fixed effects is on each country as opposed to the individual that we were talking about before. And when you do that, you come out with this this result, which is basically saying for every percent increase in my GDP per capita, the average life expectancy goes up by like 9.7 years. Or maybe the log of that. Yes, that's right. That's right. So 1% increase in GDP is, causes a 9.7 or 9.8 year increase on your average life expectancy. Okay. And that is causal in the sense that we have control, right, for all of the possible variation between countries by including that as a fixed effect. Yes?
Does that also include differences between countries that change over time?
No, it would not. Yeah. And so if you suspected that there are other things that might affect life expectancy between countries that change over time, those would not be captured by the fixed effect. Okay. And we can do it in the other way as well, right? Which is to include a dummy variable for every possible country. And so that's actually what this line 28 does. You can see the difference between line 28 and 23 is instead of looking at the demeaned version where you've taken out all of the between country variation, instead we include this additional variable factor country, which is including each country as a dummy variable, right? And that's the alternative way of doing this one-way fixed effects plus our log of GDP per capita. And so if I run that, we can see here in this table, now I have a coefficient associated with every single country. Okay, and so that is each country's, right, separate intercept in terms of where they kind of start for life expectancy. And if I go all the way down to the bottom, we'll see log GDP per capita, right? So this is our treatment variable, and we observe it's 9.8. It's the exact same value as in our other model. So they both will give the same thing. And with regards to all of these things. The reason why this particular technique is not employed as frequently, right, is because we don't actually really need to list out all of those controls. They are, no, you're not gonna go through all of those values and do anything kind of meaningful with them. Okay. Any questions? If you did catch a glimpse at the like R squared value, you will notice that they are different. And in fact, this one has a much higher R squared. And the reason for that is because the model is actually capturing different things, right? So this is thinking about how much of the overall variation in life expectancy that's being captured, whereas the other model is thinking specifically about how much variation within each group is being captured, not including the like country by country effect. And so your R squareds will be different between the two models. Okay, let's take a quick 3-minute break before we move on to our next technique. Hey.
I have a question about my course project.
Yeah.
I found this data set, which is from PAM data, contains information about the flow, the speed,
Okay.
occupancy. I have a question that can I use this data set for doing some time series analysis, for example, for predicting the flow? Because after I analyze PAM's data, we see a lot of missing value in their system, and I think this.
You want to like fill it in, basically.
Yeah, for example, and now I try to, for example, write some models, like some deep learning models, to predict this flow.
Yeah.
For example, comparing different models to finding the best model for evaluating and predicting.
Yeah, yeah, that sounds fine. Yeah.
Because the last time that I went to your office, we talked about LMPs, and
Yeah.
I tried to find some connection between LMPs and some
Right.
translation area, but I couldn't, because
Yeah.
that area is far from, for example, EVs.
Yeah, yeah, yeah.
Because when you want to analyze EVs, and you need to consider different prices.
Yeah, yeah. So work with this a little bit, see how it goes, and
So
yeah.
you mentioned this data set is better.
I think so. I think it looks, yeah, like you've got a lot of information
Yeah,
here. So.
this data is from one of my course in my first quarter.
Okay.
Another course, and I collect this data from PAM's data. It contains information from until
Yeah,
last
yeah.
month.
Let's talk more after class.
Okay.
Yeah. All right. Let's continue. So I'm gonna make. All right, so let's talk about a technique called differences in differences. So let's say you have some kind of treatment effect, and that goes to some kind of outcome that you're trying to measure. And let's actually suppose that this is a particular type of treatment that you can observe coming into play over time. Okay? And so let's say you have a group of individuals, and then let's say you want to okay, let's say all of these individuals are sick in some way, and you have a treatment which is some kind of like medicine that you give them. Okay, and so you have a group of 100 people, they're all sick, you give 100 people all medicine, and then you observe how they get better. Okay, so you observe that a bunch of these people get better over time, and can I attribute the effect of my treatment or medication on their getting better? What do you guys think? You're shaking your head, and why are you shaking?
Other reasons why
Huh?
there could be other reasons.
Yeah, so even let's actually say that you've like isolated all 100 people, and you get to control everything that they do, and so there's no sort of external factor that may cause them to improve in health.
It could still be time.
Yeah, exactly. So you don't know if they're just getting better over time versus that's the effect of the treatment, right? And so you unfortunately have this kind of, unfortunately you have this backdoor that would be kind of hard to get rid of, right? Because you may see there's some effect happening over time. Because maybe sick people just get better over time. And so what might we do to try and control for that? Yeah.
Look at the trend in a group that's not given the treatment.
Yeah, exactly. And so I'm going to include group here, which at first glance makes it look like you've made the model worse or harder, because now you are adding a backdoor. But in fact, this is kind of a clever way in which we can observe, in this particular case, sort of trends over time in both groups, control for that to isolate the effect of just the treatment. Okay, and so those trends over time we call as this parallel trends assumption, which is that group of untreated individuals, whatever effect they're observing over time, we assume is the same effect that would be getting observed over time for the treatment group. Okay, so this is a method of controlling effects by observing groups undergoing treatment versus groups that never undergo treatment. So one, we isolate the within variation for treated and untreated groups, closing the back door. And then 2, compare variation for treated group to within variation in untreated group. And this controls for time differences and closes the back door. Okay. So let's look at a sort of practical example of this. All right, so the year is 1849, and we are looking at 2 areas in London. Area 1, London, Area 2. Does anyone happen to know what disease is running rampant through London at this time? Yeah.
Just a wild guess, cholera?
Yeah, cholera. So cholera is a
Waterborne.
waterborne bacterial disease. Coming from the fact that you have dirty water, usually poop water, and so this leads to a lot of deaths. And there happened to be this kind of interesting intervention that happens around this time period. I'm going to call this the Lambeth intervention, where someone made some observation about whether, or it was testing a hypothesis about whether or not the dirty water was actually related to cholera disease. And so this particular intervention changed the water source for this particular area in London, and they shifted the water source to be actually upstream of sewage, right? And so you have, so shifting water source upstream. So here we have some kind of change in cholera. So London, Area 1 again. This time in 1854, you have a measurement of death rates after the intervention was applied compared to changes in cholera with no treatment. So in a different area of London, there was no shift in the water supply, and so we see something, a conceptual model looks something like this. Okay, and so if you actually look at the data, so we have death rates in 1849 versus death rates in 1854. And you have non-Lambeth, so this is Area 2 versus Lambeth in Area 1. So in area 1, the death rates in this area were at 130.1 and went down in 1854 to 84.9. Okay. I think this is deaths per like 10,000 or 100,000 people. Don't remember exactly. So 130.1 going down to 84.9. And the question is, can I actually attribute this decrease in deaths of what, 30 plus 15, 45, so 45.2 decrease. Can I attribute all of that to my intervention, my treatment, which is shifting the water source upstream, right? And unfortunately, you don't know whether or not all of this came from the intervention or if this was sort of naturally coming from some changes over time. But luckily, we have data from another like similar area that didn't see a treatment. And so there we see 134.9 to 146.6. Okay. So if it were the case that there is this parallel trends assumption happening, then the expectation would actually be that this number should actually increase over time absent the treatment, right? And so in this case, this area C goes from 134.9 up to 146.6. And so if the parallel trends assumption holds, then what we would expect to see here, absent treatment, would actually be an increase of 11.7, right? So this is plus 11.7. And then what did I say? This is minus 45.2. Okay. And so the differences is actually taking this difference and then taking this difference as well, right? And so actually, treatment effect would be 84.9 minus 130.1 minus 146.6 minus 134.9, and that is equal to negative 45.2 minus 11.7. So our treatment actually yields a change in death rate of 56.9. Okay? And this captures the sort of effects of changes over time to more accurately assess the effect of the treatments. Yeah?
But I have to somehow consider how big the starting point is, because if it's like it would be 1,340 and it would be plus 110.7, and the effect would be much stronger just because the size of the first group is much bigger.
Yeah, so that's related to what you assume about the parallel trends, right? And so if you wanted to consider it, if you wanted to consider kind of the magnitude, then you could always like scale it, right? Yeah. In this case, I actually think that this is the appropriate way because it's all measured on a per capita basis.
The fact that it's a rate kind of
Yeah, it's already a rate.
adapts to how big the populations are. Although there could be an effect of like a larger population has a higher death rate, so the disease spreads faster.
I think it would have to do with like density. Oh, I don't know. Anyways, there are ways to kind of fudge your, or not fudge, but like change the way you assume the parallel trends are happening to accommodate. So if you wanted to, you could like do normalization and other things. But the general idea is that the expectation is that the effect has to be happening the same in both groups, both treatment and non-treatment groups. Yeah.
So the parallel trends assumption is if you have like two similar groups
Mhm.
and say like you do nothing to both of them, they will change in the same way over time.
Correct. Exactly.
Okay.
Yep. And that assumption may not always hold, and in those cases, you might have to figure out, yeah, a different way of doing it. Okay. So I can actually write this particular thing that I just did here out in regression form. So when you have two groups, well, it should look something like this. So how to y is equal to where you have a effect by group and effect by time. And so these are the two things that you are differencing against. And if you have it out like this, then your beta 1 will actually give you the exact effect of the treatment. And when you have specifically two groups, this is the same as y equals beta 0, beta 1, treated group, plus beta 2 after treatments, plus beta 3 treated group times after treatment. And actually, this particular form is actually a version of a fixed effects, because your treated group and your after treatment groups are both fixed effects groups, and so this is actually commonly referred to as a two-way fixed effects differences and indifferences. So yeah, you can actually set out the model to run a fixed effects that will give you essentially the same thing as a differences and well, it is the differences and differences. It'll give you kind of the same answer. Okay. Let's jump back over to the code. Yeah, so let me talk about this particular example. So in in most states in the US, you are by default opted out of being an organ donor. Okay? And so, you know, if you don't do anything and you pass away, by default, you would not be sort of donating your organs for sort of medical use and, you know, implant for someone else. But some states allow an opt-in choice, right? And so you can, if this is most commonly done through like driver's licenses. So if you you actually are presented with an option that says, hey, actually, I do want to be an organ donor. And if you don't do anything, then you're opted out, right? So this is what's known as an opt-in. And so California in particular introduced a kind of a third option in 2011 known as active choice, which is that rather than having a sort of default stance on opt-in versus opt-out, it presents you with a choice on whether or not you want to be an organ donor. So a yes or no as opposed to a default choice, right? So do you guys see kind of the distinction here? So instead of saying, yes, I opt into an organ to be an organ donor, it says, it presents the option, yes, I want to, or no, I don't want to, right? And so now there's no like default option. You have to choose one. And so there's the question of, does using an active choice mechanism cause people to more often become organ donors? Okay, and so this is kind of a case that we are able to do this difference in differences because we have this treatment that happens at a specific point in time, and then we can compare against organ donation trends in other states that happened over time to see whether or not this particular treatment option of presenting an active choice causes more people or less people to opt in or out. Okay. Okay, any questions about that? Actually, I think there's a nice little graph of this. Give me one moment.
What's the vertical bar in the function model for your model?
I'll talk about that in just a second. Okay, so here, in this plot, we observe when the treatment happened, which is the introduction of the active choice model. And the black line is the observed rates of organ donations over time in California. And you can actually see that it actually goes down a little bit. And then the dotted line is the average trend for all of the other states that don't see treatment. and it actually goes up a little bit after the treatment event happens. And so the parallel trends assumption would be that California acts like all of these other states, okay? And actually, in the other one, yeah, here you can see the sort of before and after for the untreated group, and it actually goes up. Which means that actually, when I subtract away the before and after time period in my untreated group, and so you're essentially lowering the gray line to what it looked like before, and doing that subtraction to the California group, that results in actually a larger decrease. And so you end up actually going down in the number of the number of people who choose to become organ donors after the active choice treatment effect. Okay. And so that's what is happening here. So the way that we're doing the fixed effects, this particular example of differences in differences, because you're doing one with just two groups, you can do it as a fixed effects, as I was mentioning before. And the way that you write it out is you have your treatment in front, and then in fixed effects, this vertical line, right? Yeah, this vertical line separates your variables, your explanatory variables from the fixed effect groups, which are state and order. Yeah.
What's the logic behind choosing like the quarter as one of your fixed effects? I understand the state, but
so we have two groups of things that we want to control for, right? Which is the group of states and the group related to changes over time. So there's two fixed groups that you're controlling for. And when I run this, the effect of the treatment is essentially telling me that my organ donations decreased by 2.2% kind of directly as a result of introducing active choice as the way you opt into becoming an organ donor in California. So this kind of simple regression model, if we believe the parallel trends assumption, is a pretty powerful way of inferentially coming up with the causal relationship between our treatment and our outcome. And particularly interesting given that the choice to pursue this active choice mechanism was explicitly meant to try and increase people's or increase the rate at which people would opt into becoming an organ donor. And in fact, it kind of did the opposite. Okay. Any questions? All right. the last one that we'll look at today is the instrumental variable. Okay, so if I have my treatment going to y, and I have some unobserved latent variable that is preventing me from really being able to isolate the effect of x on y, it turns out that if you have a variable that affects your outcome only through the treatment option, then it can remove any part of the outcome that is not explained by the instrument. So it cuts out the effect of your U, essentially. It's a very powerful tool because you can have any number of these like unobserved things that can be happening related to your outcome. And we talked about how difficult it is to try and isolate all of those things. If you find a good instrumental variable, it kind of lets you bypass all of that, right? And so this is a variable that affects your treatment and your outcome only through the treatment. And this can remove any part of the outcome that is not explained by the instrument.
So you're just kind of replacing the treatment with the instrument?
No. You are essentially what you're doing is you are isolating the specific effect of your treatment on the outcome via the instrument. Let me do an example and maybe it'll become clearer. So let's say I'm interested in an outcome of BMI and I have a treatment of whether or not someone is a smoker. So this is my treatment. So unfortunately, you have a whole bunch of possible things that could be affecting someone's BMI besides whether or not they smoke, right? And so you might have something like income or age, gender, whether they're pregnant, their level of education, right? So there could be a whole slew of different variables that may affect your BMI, your body mass index, besides smoking. And if you wanted to isolate the effect of your treatment, I would ordinarily have to control for all of these things, right? And in fact, you probably have some things that are related to the prevalence of you smoking, right? So someone's income or age or gender, education, these could all be related to your smoking. So you have all these like possible backdoor paths that you'd have to close. And in fact, we could have a latent variable that does this. So this is the difficulty in the instrumental variable, is that how can I find some good variable that will affect only smoker, but you cannot have any of this stuff happening, right? Or this stuff happening. Okay, so if the instrumental variable affects other things on a path that goes to BMI, then it doesn't work. Okay, so let me ask you guys. So what about something like unemployment? Would this be a good instrumental variable? You're shaking your head. Why not?
Because it's related to income, probably, maybe to gender too.
Right. So your unemployment status is probably pretty heavily correlated to income or related in some way, right? Yeah, it could be related to gender. Age, obviously, right? Okay, so maybe not great. Okay, what about if someone is separated or divorced? Let's say at least. So step one, do we think that people who are separated or divorced might be more or less likely to be smokers? Maybe, right? And so there you have the first connection, but then there's a question of,
Could be depressed and eat more,
yeah,
or less.
okay, yeah, and so maybe there's something going on with the you, right? You go through some diet that you maybe don't observe. What about how it might relate to, so separated or divorced, that might actually relate to the likelihood that someone's pregnant, right? Okay, so also this instrumental variable, even though it does do this thing, I'm worried that it would do this as well. Okay, so in that case, no good. Okay, what about whether or not there's a cigarette tax? So if you have a cigarette tax in place, would that affect someone's predisposition towards smoking? Probably, maybe, right? We'll say that if you are sort of price sensitive, right, then introducing a cigarette tax may actually cause someone to smoke less or not smoke, right? What about how a cigarette tax would relate to any of these other things?
Related to, because maybe it's a different state where the income is higher.
You're killing me over here. Let's just pretend, right? So this is also why it's hard to get a good instrumental variable, because we've got people like Simon who are like, oh, what about this? Yeah, Christopher, yeah.
Would buys cigarettes be a good instrumental variable?
But that would be the income again.
Yeah, I don't.
That's an outlier.
Yeah, I
If
think.
you're a smoker, you buy cigarettes.
Yeah, but that's going to be related to a lot of these other things, right? In the same way that these things are related to the fact that someone might smoke, that's going to be related to whether or not you buy cigarettes. Yeah, so the cigarette tax, yeah, generally there's this weird income argument, but we're just going to put that aside for a second. Generally, we would say that cigarette tax is probably not sort of causally related to, all of these things, especially at an individual level, right? Because yeah, even on that argument, I would actually say, the sort of individual level variation would probably still let you get away with it. Anyways, So the idea is actually, if I can regress whether or not you're a smoker on cigarette tax, right, then I can see how much this part changes only due to the instrumental variable, and then observe the changes to BMI in that way. And that would let me, again, right, isolate just that sort of marginal effect coming from my treatment group. So the common way we do this is via something called two-stage least squares. So in an OLS, we would have y equals beta x plus epsilon. In 2SLS, we have stage 1. Your instrumental variable regression will do x, and this is our treatment, is equal to your instrumental variable. I'm using different variables from beta and epsilon because this is denoting a difference regression, and a lot of textbooks use delta, and I think that's zeta. So if you estimate this thing, I can then generate x hat based off of my calibrated coefficient, right? And then in stage 2, I would just run my regression as normal, except that I'm going to be including my predicted values for x as opposed to the observed values, okay? And I'll just comment that even if you have a valid instrument, which is born out of us making this like model and justifying it, oftentimes if your instrument and your treatment are kind of weakly correlated, you can introduce a lot of noise into the model. Okay. So the last thing we'll do is
Please reiterate what you're actually trying to accomplish with the instrument variable. I still don't see the point.
yeah.
Like, if only smokers are affected by the cigarette tax, then that just feels like it makes
Because in this causal model, I have so many things that could be affecting smoking and BMI. If I were to just look at whether or not someone smokes, I would be pretty hard pressed to identify whether or not changes in the variation in their BMI is because they're smoking as opposed to any of these other factors, okay? And so I need to come up with a clever way to figure out some way of isolating the effect of smoking on BMI. And the way that you do that is by using an instrumental variable that can operate on your BMI only through the treatment, right? And so seeing a cigarette tax in like one state or city compared to another, I can be confident that the variation in BMI in the city that sees that cigarette tax versus like a place that doesn't, that the variation in the BMI is specifically happening through my treatment as opposed to through these other things, right? And so even though in one place you may see variation in income, age, gender, and whether or not they're pregnant, and education, what you're basically saying is that it's not the cigarette tax that's causing someone to have higher or lower income, or having someone to have slightly different education, or having someone to be, different genders or pregnant. None of that stuff is happening because of the cigarette tax, right? And so the idea is that if I observe changes in the BMI that are kind of the concept is like that those changes are being observed in conjunction with differences and variation in my cigarette tax, then I can be confident that that is specifically related to whether or not people are smoking, as opposed to any of these other things. Yeah.
So, can I just use the cigarette tax as the treatment, and then smoker becomes like the
Yeah, that's what I'm saying. You're just
Yeah.
making the chain longer.
Except that the treatment isn't the cigarette tax. The treatment is the smoking. So if you were to just randomly change cigarette tax, that wouldn't cause changes in BMI unless it were through smoking, right? And so this is the idea that that if I wanted to know specifically the effect of smoking, right, what would that do to BMI? So you're right in the sense that you could use an instrumental variable to see how it changes BMI, but that wouldn't tell you anything about how the treatment is affecting BMI, which is the thing that you care about, right? So it has to do with your research question. And my research question is not how much does cigarette taxes change BMI, it's how much does smoking change BMI. Yeah. And you can think of that as being as a useful policy, right? Because, a doctor could be like, hey, you should stop smoking because smoking will do this to your BMI, as opposed to something like, oh, I'm going to pass a cigarette tax in order to get people to have like a lower BMI, right? Okay, I guess we're out of time, so I'm gonna go through the example of how to implement the IV at the start of class on Wednesday.
Two questions.